Steve is going to present to us a talk describing how system engineering across the life cycle can be made more rigorous with ontological rigor. Okay, Steve, go ahead. We can't hear you, Steve, yet.
Okay, can you hear me now?
Yes, we can.
Okay, so let me see if I can share. Okay. Greetings to everybody from the Fairfield Inn and Suites in Collierville, Tennessee, where we are on the road. Are you seeing my screen?
Yes.
Do you see it full screen now?
Yeah, you're good.
Okay. Good. Excellent. Okay. So it's kind of a broad topic, but let's just jump right in. I am not a visual thinker, so I like to think of my slides as extremely friendly for the vision impaired. They consist of nothing but alt text. So I want to start with just a few preliminaries. So the first is my usual mantra. So I'm talking about ontological modeling across the life cycle. So I'm going to start out by telling you what I mean by these words. And these are not attempted to be definitions. I don't like definitions. I think they're a waste of time. This is just a shorthand. The word modeling means something in this context, and here's what it means. It means three practices: using precise language to communicate more effectively, using mathematical abstractions to make our analysis more powerful, and using computers to do things that they're better at than humans. Anybody who's heard me speak has heard me say this. I think that's just engineering. And if you're not doing those three things, I don't think you're doing engineering in the 21st century. So the whole term model-based system engineering is redundant, and I wish we would stop saying it. It's just engineering. You have to do all of this. But that's what I mean by modeling. What I mean by ontological is that this precise language is specified in the form of a grammar that scopes what is a meaningful utterance. So, for example, in some domains in engineering, for example, in mechanical engineering, it's perfectly meaningful to say that a certain part, say a strut, has mass 12 kilograms. And that's meaningful because strut is a defined class. Mechanical engineers know what a strut is, and they know that struts, it makes sense for struts to be in the domain of the relation has mass, and that this particular thing belongs to that class, and therefore it's meaningful to talk about it. And has mass is a relation whose range is a quantity value of quantity kind mass. And 12 kilograms is a well-formed quantity value of that quantity kind. So there's all sorts of things that it would not be meaningful to say, even though they're syntactically correct. I mean, it would be correct to say strut S has mass 3 liters, but that's semantically wrong because 3 liters is not in the range of has mass. Similarly, it's not meaningful to say that a function has mass because function is disjoint with the domain of has mass. So what I mean by ontological is that we're talking to each other in a language that has rules, and those rules scope what is meaningful to say. Now, I want to be clear, the rules do not tell you what things actually mean, right? The vocabulary does not tell you what mass means. It says it's meaningful to say a strut has mass. And if you say that strut has a mass, then there may be logical consequences that a reasoner could draw. And for example, if that strut belongs to some higher level assembly, then that 12 kilograms is also part of the mass of that higher level assembly. So we're using rules to define what we're allowed to talk about, and we have some sort of reasoning system that lets us draw inferences from it. And I'm a big fan of the particular subdomain that OWL implements called description logic, because in description logic, we can show that the reasoners are both sound and complete. What sound means is they do not draw any conclusions that aren't true. And complete means if a conclusion is true, then the reasoner will draw it. That's useful. So that's what I mean by ontological in the context of modeling. And what I mean by across the life cycle is simply what we already know, that big systems need life cycles. You don't need a life cycle to, go have a drink. You just go do it. Big systems need life cycles because for a lot of reasons. One reason is that big systems entail complex behavior that we only can get at through multiple layers of functional abstraction. We start out at the top saying, gee, we'd really like to do some planetary science. And from there, we design systems. And from there, we design assemblies. And then we design electronics and mechanics. Eventually, we're doing low-level physics, but we started out doing sort of global science, and there are interfaces at every one of these layers. Similarly, this complex behavior spans multiple intellectual disciplines. So we have to talk about physics and chemistry and biology, but we also have to talk about psychology and economics. Can we build this thing? Can we afford it? Can we convince people that it's worth building? And again, there are interfaces at all these boundaries. And finally, big systems just last a long time, and they may outlast individuals and organizations. And, to use some examples that we're all more or less familiar with, the NASA Voyager program was proposed in 1972. The spacecraft were launched in 77, still flying today. 53 years later, lots and lots of people have retired, and some of them passed on since that program began. So it requires more than just what a small group of individuals can manage. Similarly, the Large Hadron Collider, involves 10,000 scientist contributors. So just no way to do that without some sort of a life cycle. So by across the life cycle, I just mean any place there's an interface like this. Ontological modeling is useful. So a few more preliminary notions. Again, I'm just going to use words in this way. This is pretty standard usage. A quantity is a measurable property of some object. So when we said something has mass 12 kilograms, the mass of that thing is a quantity, and 12 kilograms is a value of that quantity. And this is consistent with the terminology of the metrology experts in the world. And then to sort of specialize that a little bit into maybe some JPL specific usage. Well, not really JPL specific, but we use parameter to talk about quantities that don't vary over time, like the mass of a piece of hardware, and state variable to talk about time varying quantity. And then a constraint is simply a relational expression that involves one or more quantities. So mass less than 2 kilograms or kinetic energy equals 1/2. Oh, wow, I got that wrong. MV squared, please. And F equals MA because, quantities can be time varying and mathematical functions of quantities like derivatives are also quantities. So acceleration or the second derivative position is a quantity. So I'm using the word constraint simply to mean a relational expression involving one of those. And it just because you say it doesn't mean it's true. It may be true, it may be false. And we'll see some examples of that. And then I'm simply going to use the word scenario to mean a named set of constraints. It's just a shorthand we use to say, well, that stands for this set of constraints. And this ends up being useful in doing some pretty common stuff in systems engineering. So again, this is all just preliminary stuff. So there's a branch of logic called modal logic, and they expand beyond purely true and false, and they talk about things being possible, necessary, contingent, and impossible. And we don't need to go full modal logic here, but these are useful to think about. And when we get to the example I'm going to work through, we'll see that this is a useful way to think about these constraints or these propositions, is they might be possible, they might be necessary, contingent, or impossible, etc. I'm going to skip over this. We're going to do a simple example with quantities and just linear quantities or scalar quantities, but you can actually go a little more general than that. You can talk about like membership in a set or saying that this thing is made of aluminum. It doesn't have to be, the examples don't have to be as simple as the one I'm using to illustrate today. And then I do want to talk just briefly about whether systems engineering is additive or subtractive. You know, do we start from nothing and add things till we have a system, or do we start with the universe and remove things? I firmly believe that it's the latter. We start with the universe and we remove things that are unacceptable, because we don't want to just design a system. We want to describe a space within which there are multiple acceptable realizations and hand that to our suppliers and say, okay, be clever, find the best one in here. And we can give them preference functions. We can tell them what we like better than other things. But I think our job is to define the space, not define a point in it. And the way we do that is by imposing constraints. So we start with all possible outcomes and we throw out the ones that don't satisfy the requirements. And then we throw out the ones that cost too much. And we throw out the ones that have too high failure rates, et cetera. And eventually we end up with a space in which we're happy with anything in the interior. I'm going to skip over this too, except to say I really don't like the phrase single source of truth, because truth is very slippery philosophically, and we don't really need it. We talk all the time in systems engineering about things that aren't true, and we hope very much they are not true. For example, we say, assume the primary radio receiver has failed. Well, it's not true that it's failed, and we don't want it to be true that it's failed, but we are very interested in knowing how the world looks if it has failed. So I don't like referring to models as truth. Models are just assertions or constraints in context, and the context tells you everything. So with that brief set of preliminaries, I want to look at the familiar V that we've all known and loved many times, and think about the what I called information precedence. At one level, someone is saying the system shall be something, and based on that, some people go off and design subsystems and say, well, the subsystem shall be. And based on that, a bunch of other people go off and design lower level things, and they say, well, this is what the assembly shall be. Now, these arrows are precedents. It doesn't mean the system shall be information becomes part of the subsystem shall be. It means that the system shall be is essentially governing, and the subsystems have to be compatible with the system, not the other way around. There's a precedence there. And similarly, when we build up the real systems and do the integration and testing, the reality about the low level things really takes precedence over the reality of what the intermediate level things are, because they get their reality in part from how the low level things are, and in part as to how they're composed. But the precedence goes the other way, and everybody knows this, right? You go down one side of the V and you go up. When you do system verification or verification at any level, you've got a verification report, which is this. I don't want to say this is the process, this is the product, but there's a verification process that produces this information and says, okay, things are verified here. And that takes the process of verification is literally looking at what something shall be and what it is, and reasoning about whether those are consistent. And if it is something that it shall not be, then you've got a problem. Or if it isn't what it shall be, then you've got a problem. So and again, we all know this, that what it shall be and what it is, or what it takes to verify. Now, note, there's no arrows going up from here. The verification report from assemblies isn't really part of the verification. It doesn't take precedence over the subsystem verification. Each of these is done independently, but this verification is the only reason that the assembly producers stand behind what, these assertions about what they are. So that's, again, nobody should be surprised by this. But what are the temporal implications? So if we put all the arrows on the chart and say, what does this mean in terms of how we implement the life cycle? Well, the traditional waterfall that everybody loves to sneer at and mock as a ridiculous idea, even though no one ever really recommended this, is that the precedence relation, the temporal precedence, is the predecessor has to complete before any successor begins. And of course, that won't work, and everybody knows it won't work, and that's why we all scoff at it. But in fairness, no one was really ever pushing that. Yeah, we all know this. I mean, there's this big bow wave of integration. When you try to do it that way, it doesn't work. Everybody knows it. You can just relax the criterion and say, well, it's not that a successor can't start before the predecessor completes. You just say a successor can't complete before its predecessor has completed. And what that really means in practical terms is verification can begin a lot earlier. So as you can see, I'm not much of an artist, but the verification process are pulled to the left and can begin earlier. Okay, great. But what can we do? What can we do to do systems engineering earlier in the life cycle? We don't have a system to verify. Well, you can do a lot. And software developers figured this out a long time ago. They had the big bow wave of integration. And this is where the whole idea of continuous integration and testing comes from. So it's important to bear in mind that those arrows are logical precedents, but that's not the same thing as temporal precedents. And we are not going to do one final, complete, all-up system verification and be done. We're going to do lots and lots of partial system verification, and only the last one has to be final and complete. And ontological modeling really helps us go through this. So instead of doing this one big, system shall be eventually percolates down the V and back up to what the system is, and we do verification, we're going to do one after another of increasing scope and specificity over time. And only the last one has to be complete. So let's take a look at what that looks like on a simple problem. So let's assume we need to specify a telemetry system for a Mars mission. And we need to talk about a system that's going to include a spaceborne transmitter subsystem and a ground-based receiver. And our job is simply to write requirements to a system supplier who's going to build this, system for us and give it to us. We want to write the specification. We want to ensure that the receive system satisfies its requirements. So let's make up a couple of requirements. Well, one is just a requirement on the bit error rate, and that turns out that's kind of that's the kind of requirement people actually write on telecom systems, and it ends up to have some interesting. There's reciprocity relationships. The louder you can transmit, the less sensitive the receiver needs to be. But let's just look at what a requirement like this might look like. It might say something like, during the Mars orbital tour, except during conjunction, at the nominal bit rate, the telecom system bit error rate shall not exceed 10 to the minus 5. So let's take the last part first, because that's the easiest. So bit error rate is simply a quantity. It's a measurable property of the telemetry system. And values of the bit error rate are expressed in units of 1. If you read ISO 80,000, these unitless or dimensionless quantities are actually, they're called units of 1. And the expression bit error rate less than or equal 10 to the minus 5 is a constraint. Is it true? Well, not necessarily. In fact, our customer is paying us to make it true. So in modal logic terms, what we really need to do is arrange the world and so that it is necessary that the bit error rate is less than or equal 10 to the minus 5, and therefore it's true. And the goal of system verification is simply to show that necessity, that the system is such that the bit error rate satisfies that constraint. So that's the second part. Let's talk about the first part of the requirement, this during part. What does during the Mars orbital tour except during conjunction mean? Well, we can just think about that again in terms of constraints on quantities. The Mars orbital tour is again a scenario. It's just a named set of constraints. And the constraints are that the range, I mean, I'm making things very simple here. The range is 2.2 times 10 to the 8 kilometers, and the Earth-Sun angle is greater than 15 degrees. You don't want to point your antenna, your telecom antennas at the Earth when the sun is between you and the Earth, or even when the sun is behind the Earth. If it's right on the same angle, that is during conjunction, you just don't want to do that. It heats things up and things don't work very well. So we have to sort of guard this requirement to say we're not going to expect that kind of performance during conjunction. So we want to say when you're at Mars, that is, you're not at Jupiter, you're not any farther away than 2.2 times 10 to the 8 kilometers, and you're not pointing at the sun, and at or below the nominal bit rate. Why do you have to say that? Well, the faster you try to transmit, the higher the bit error rate goes. So we're telling them, okay, let's assume the nominal data rate is 2 megabits per second, and at that rate, we want to see 10 to the minus 6 or 5 bit error rate. Good requirements often look like this. They have a set of scenarios under which the requirement applies. That second bullet, that's my words, but I don't recognize it. Okay, a scenario, again, is just shorthand for a set of constraints that say the requirement applies during this time, but otherwise not. And then some things that are actually required, which are also constraints. So that's one requirement. That's sort of a performance requirement. Let's assume we've got one other requirement that is simply on the mass of the spaceborne side. We don't care what the ground system weighs, but we're going to say we want the spaceborne elements to not exceed 20 kilograms. What's the applies during? Well, in this case, well, it's always. So when it's unstated, we're going to say it's always, but we're going to make it explicit when we encode these requirements. So if we wanted to pass this shall be information down from the customer to a supplier, we need a syntax for that. Let's come up with a convention. Let's say we're going to send them a JSON file and send them a schema so they can check to make sure it's okay. Well, what does that need to contain? Well, it needs to tell them the definition of every quantity that we care about, the definition of every scenario that's implicated in any of the requirements we're sending them, and the constraints that scenario entails. So we're explaining the shorthand. When we say, during Mars orbital tour, except during conjunction, these are the constraints we mean. So the list of quantities, the explanation of the scenarios, and then the requirements and listing for each requirement. What are the scenarios on which it applies? And are the constraints that it requires? So if you did this example in JSON, and again, this is super oversimplified, but there on the left is simply a list of quantities. There's the range, there's the Earth-Sun angle, the bit rate, the bit error rate, and the spaceborne mass. Those are all the quantities that got discussed anywhere in those two requirements. And you see there's just this dummy shorthand to say that we'd say a lot more about them than their name. We would say what kind of a quantity they are, blah, blah, blah. And then here are scenario definitions on the right. And again, there's just two. One is called Mars orbital tour except during conjunction. The other one is called, there's three. The other two are at or below nominal bit rate and always. And again, for Mars orbital tour, that entails two constraints. One of them is range less than or equal to 2.2 times 10 to the 8 kilometers, and the Earth-Sun angle greater than 15 degrees, et cetera, nominal bit rate. And then the always entails nothing, but that's actually correct, because remember these constraints are restrictions. So if we're not restricting anything, then it applies always. So the entailments for always is just empty. And then here are two requirements. So the first one is ID R1. It applies during those two scenarios, and it requires that the bit error rate be less than or equal to 10 to the minus 5. R2 applies always and requires that the spaceborne mass be less than or equal to 20 kilograms. Now, this is utterly trivial, but it's precise, and we really don't need much in the way of vocabulary to do this. Now, obviously, you need more constraints than just these simple inequalities, but this illustrates the point that if a constraint simply has a name that embodies some mathematical relation that something like Mathematica or MATLAB knows how to compute, then we can be even, we can have richer descriptions than just these simple things. But this is all the vocabulary it took to encode that. And if we do this, then we can write very simple code to generate this shall be, that is the requirements packages for our suppliers. And not only that, we verify that the package is well formed with widely available free software tools. So we're going to be very careful and not send anything to any suppliers that we haven't validated. And we're going to encourage them, as soon as they receive it, run that same validation. And this is the way we build confidence in each other. And when you build confidence in each other, and you build trust, and we simply reduce the risk of fooling ourselves and our suppliers by writing requirements that neither of us understand. We're encoding what these requirements mean, not what they say. And that's a big difference. We can do very similar things with the is information, which is rolling up the other way. This is a little trickier because the is harder to produce because some of these constraints, like the bit error rate, is not simply a dial that you turn on a telecom system. It's a computed property.
Steve?
It involves a whole bunch of other stuff. Yeah.
Yeah, just if you can wrap in a minute.
Yeah. It involves a whole bunch of computed stuff that is complicated to do. So it's not trivial to produce it, but you can do the same sort of thing. The is information is shaped differently because we develop it during testing and during simulation. So I'll sort of skip to the conclusion here. The is information is sorted differently. The outer sort is by scenario sets, because that's how we collect this information, and that may be how we verify it too. We want to simulate Mars orbital tour at or below the nominal bit rate, and then observe our system through simulation or testing and whatever. Here's a case where the bit error rate is 8.2 times 10 to the minus 6. That satisfies the requirement. Some sort of an automated verification check would conclude, you're good. So the verification is now trivial if you're moving this information back and forth with this more precise semantics. And I don't want to oversell it, right? Producing the information in this form is not trivial, but having established a custom for exchanging this information in a rigorous, syntax and semantically rigorous way means that we can start practicing verification from day one. On day one, we're just going to be running the verification mechanism on empty but syntactically valid shells, and we'll start getting the pipeline set up. And then we move to rough order of magnitude approximations, and then we move to simulations, and then we move to hybrid hardware in the loop testing and full up system testing and digital twins. As we move forward, the information gets richer and richer. But just like in software, you're not allowed to break the build. You must always produce valid information. It's okay to violate a requirement, but you can't break the verification process. And running verification early and often is how we trust it when it matters. So I'm going to skip that. Just say really quickly that your engineering doctrine tells you what needs to flow across these interfaces, and that's how you scope your model. If your model can be used if you can ingest anything anybody sends you that you rely on, and if you can produce anything that anybody relies on from you, then your model is complete, and you don't need to do a thing more than that. It's satisfied the job. So this is the final slide. So if you're doing this ontological modeling across the life cycle, it really channels your intellectual effort into producing the knowledge that your process needs to succeed. And you need to focus on and build consensus around what do I rely on from others and what do others rely on from me. And if you do this right, then things just match up at the boundaries and we shorten this gap between design and verification. And eventually, what we really want to do is not think of those as separate processes at all. That design simply includes planning for, preparing for, and practicing verification from day one, and practicing in both sense of the word, rehearsing and executing. And like Martin Fowler says, if it hurts, do it more often. That's it.
Thank you so much, Steve. Is there any questions to Steve at this point? All right. Great.
I hope none of that was a surprise to. I hope none of that was a surprise to anybody.
No, I think you're. There is a question. Okay, go ahead.
Okay, thank you. First of all, congratulations. It was a great presentation. I'd like to know from Steve, how do you reconciliate if you have a life cycle with many agents with diverging definitions on their ontologies? How do you make sure that everyone is actually speaking in the same language and having the same terms throughout the process?
Well, I mean, we all have that problem, right? And I think the only way you ever get at it is to think about this notion of reliance, right? That you and I are collaborators in process. And in order to do that, you need something from me and I need something from you. And let us be precise about what that thing is and how it's shaped. It doesn't really matter what you call it. What matters is what is the thought that it expresses, right? And if I'm sending you a model and I'm calling things assemblies, but you understand that your word for a similar thing is component, and I'm not ever going to say anything about an assembly that you can't interpret about a component, then who cares what we call it? Right? What matters is that we understand each other, and in particular, we understand what we're relying on each other for.
Okay, thank you.
Thank you, Steve.